What's up guys, Matt the Maths Hero here, and I am back again with another video. We are looking at adding and subtracting fractions. It's not as hard as it sounds, so let's get straight into it. Okay, so we are going to be looking at the basics of adding and subtracting fractions today. Now if you've looked at multiplying fractions already, great. If not, don't worry. I personally think that looking at multiplying fractions before you're looking at adding and subtracting fractions is a good piece of advice. So check out our video on multiplying fractions if you haven't already, okay? But today we're looking at adding and subtracting fractions. So if you have looked at multiplying fractions, you will know that it's very simple. All we do is we multiply the top numbers and we multiply the bottom numbers. So if we have 3/5 multiplied by 2/4, then all we need to do is multiply the top numbers. 3 times 2 is 6, bottom numbers 5 times 4 is 20, giving our total of 6/20. But can we use that same trick for adding and subtracting fractions? Let's have a look. Let's have a look at a really basic fraction. Let's have a look at 1/2 add 1/2. Now we know that's going to be a whole. 1/2 of pizza and another half of a pizza is going to give you a whole pizza. Okay, so let's just see if that same tactic works for this. 1 add 1, looking at the top two numbers, equals 2. If we look at the bottom two numbers, 2 add 2 is 4. Now 2/4 or 2/4 simplified down is 1/2. 1/2 add 1/2 is 1/2. Okay, we've done something wrong. We cannot use this same trick. Okay, let's see why this does not work. We have a very important rule in mathematics, and that rule is something called the order of operations. Okay, now what that says in this rule is that we need to always multiply and divide before we add and subtract in any problem. And because fractions are just division problems, we can't do the addition before we do the division part, okay? So we can't add the top numbers and then the bottom numbers, because then we're skipping out the division part, okay? And we can't do that. Okay, so luckily we do have another trick. This is your secret tip. Don't tell anyone. Okay, but before I can tell you the trick, we need to look at a fraction and what it's made up of, okay? We have a numerator at the top and a denominator at the bottom. Our denominator at the bottom just is the name of our fraction. It's 1/5, 3/5, 5/5. It's a fifth. The value is fifth, okay? The numerator is how many fifths, the number, the quantity, how many fifths we have. 1/5, 3/5, 4/5. How many of that value do we have? Once we can understand that, once we can start to think of a numerator as the number, the volume, the quantity of the fractions we have, similar to saying 1 donkey, 3 donkeys, 5 donkeys. It's just the name of the fraction. So if we think of it like that, the numerator is how many we have and the denominator is what the name is, then we can just simply add the numerators or subtract the numerators to give us our new value. Okay, so if we look at that with our halves again, we have 1/2 add 1/2. So we're going to add our numerators. 1 add 1 is 2. But we're going to keep our denominator, the name, the same because the value of our fractions haven't changed. Okay, so 1/2 add 1/2 is 2 at the top, 2 at the bottom is a whole. Okay, then that's right. 1/2 add 1/2 is a whole. Fantastic. Let's see another example of this trick. If we had 3/15 add 4/15, we could have 3 elephants, add 4 elephants. 3 add 4 is 7. The name of the fraction hasn't changed, it's a 15th, so we have 7/15. Simple. And the good news, that works with subtraction as well. Let's have a look. If we have 5/10, subtract 2/10, what am I doing? I'm taking 2 away from the 5. 5 subtract 2 is 3. We haven't changed the value of the fraction, so we have 3/10. Simple. How easy could this be? Well, let's just pause a second. Let's not get carried away. Let's not think we are Albert Einstein all of a sudden, okay? We have got a little problem. All of our denominators are the same in these examples, okay? We had 1/2 add 1/2, 3/15 add 4/15, 5/10 take away or subtract 2/10. Now the name for this is like fractions. They are alike. We have 1/2 add 1/2. We had 3/15, had 4/15. They are like. If the denominators are the same, we call them like fractions. And if they are not alike, we call them unlike fractions. Okay, and we need a solution to adding unlike fractions. But don't worry, I would never let you down like that. There is a solution. We can manipulate the look of our fraction, give ourselves an equivalent fraction, but getting the same denominators, okay? But we're going to look at that in a different video. If you are ready for that, check out our video on adding and subtracting unlike fractions, and then we're going to learn all about how to create and transform our fractions into equal but different looking fractions with different numbers so that we can add them and subtract them. Hope this video has been helpful for you guys. Like and subscribe to the channel for weekly videos going all the way through the English curriculum, and got fun and exciting riddles and challenges as well. So please give us a big thumbs up and a like if you've enjoyed this video. For now, away. Hopefully we understand that the area of a shape can be defined as the surface that that 2D shape takes on any given surface. So for example, a good way of thinking about it is if we were looking at a football pitch, the perimeter is the white line that we can measure all the way around, and the area is how much grass we are going to need. The grass is over the surface, it's the surface area, okay? And we measure area by cutting it up into squares. So we cut the length and we cut the width into squares. Therefore, our measurement is recorded in squares. Meter squared, centimeter squared, any kind of measurement, but we are measuring it and recording it with squared. So let's have a go at a question. Let's have a go at a rectangle with sides of 4.5 meters and a width of 1 meter and 5/6. Okay, well what does that mean? Let's try and break it down a little bit. So looking at the top length of 4 meters and a half a meter. That means we're going to be cutting our rectangle into 4 equal meter width columns going across. And then the last column is only going to be half a meter, okay? And therefore the width of 1 meter and 5/6 of a meter would be split into one row of 1 meter, and the last row, that is a measurement of 5/6 of a meter, not quite a meter. So the 1/2 on the end, that's a fraction, and the 5/6, that's another fraction. When we overlay them, we can see our squares. And what we're needing to do is we're going to be measuring how many squares we have. Okay, so let's start. Okay, so where to begin? Well, we know that the area of a rectangle is length times width. But before we can do that, we're going to convert our mixed numbers into improper fractions. Why do we do that? Well, we can't multiply a fraction and a whole by a fraction and a whole. Okay, so we need to convert it into improper fractions so that we are just dealing with the fractions and we are multiplying those. Okay, so let's have a look. So how do we get from our 1 and 5/6 back into our mixed number? Well, it's pretty simple. Our unit of measurement is sixth in this example. We're looking at 1 and 5/6. So everything is measured from the sixth. So I have one whole. So let's make a bar of chocolate, split it into 6. I've got one whole of them. But in my next chocolate bar, I don't have a whole, I only have 5/6. Okay? So I've got one whole, which is 6/6, and 5/6 in the next one. So altogether, I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 11 what? Well, they've always been measured in sixths, so we're going to move it back into sixths. Okay, 11 sixths. So for my next one, 4 and 1/2, again, everything is measured in halves. So I've got 4 whole chocolate bars, which were measured in half. So I've got 1, 2, 3, 4 whole chocolate bars, and I've got half a chocolate bar. So in total, how many halves have I got? 1, 2, 3, 4, 5, 6, 7, 8, and then the 9th, 9 halves, okay? Okay, so my new improper fractions look like 11 sixths times 9 halves, or 9 twos, okay? And that is the hardest part. If you can get a good understanding of moving from a mixed number back into the improper fraction, you are halfway there, okay? Now, before we go ahead and multiply these numbers, we're going to try and simplify them. And I've noticed that we've got a 6 on the bottom row here and a 9 on the top row here. And since 6 and 9 can both evenly be divided by 3, we're going to go ahead and simplify it a little bit, okay? So 9 divided by 3 is 3. so I can change that on that top row to a 3. But whatever I do to the top row, I must do it to the bottom row. So 6 divided by 3 is 2. Now sometimes you won't be able to simplify the question, but if you can, it's always worth doing because it makes our numbers a lot smaller and a lot more manageable to see and to use, okay? So my final set of improper fractions and the ones we're going to multiply are 11 over 2 times 3 over 2. And all we do when we're multiplying fractions is we multiply the top row and then we multiply the second row. So I'm going to go ahead and put 11 times 3 over 2 times 2. Now 11 times 3 is 33 and 2 times 2 is 4. So my answer as an improper fraction is 33 over 4, okay? But because our question was given to us in a mixed number, we're going to convert it back to a mixed number, okay? Now we can simply divide this if we have a good understanding of switching between improper and mixed number fractions. So we could do 33 divided by 4 gives us 8, remainder 1. But if we need to understand that a little bit clearer, let's think about it back in our chocolate bars. So I've got 33 quarters. So I'm going to create some chocolate bars and split them into quarters and wait till I get 33 of them. So I've got 1 chocolate bar, 2, 3, 4, 5, 6, 7 and 8 chocolate bars takes me to 32. So I'm going to have a 9th chocolate bar with 1 quarter coloured in, okay? So again, I've got 8 whole and 1 left over. Now our whole fraction was in quarters, so what do we have left? We have 1 quarter. Each of these chocolate bars and each of these segments was worth a quarter. Well, 8 whole and 1 quarter. But what have I forgotten? That's right, always remember to put your measurement in. Meters squared. 8 and 1 quarter meters squared. And that's our final answer. Well done, guys. Guys, I hope you found this video helpful. Please like and subscribe to the channel for weekly videos covering all of your mathematical needs. But for now, Maths Hero gone.
What's up, guys? Thanks for coming back to the channel. Today we have got a brand new video. We are starting a brand new unit of work. A bit of a dreaded unit, but we should not dread it. This is a fun and exciting and interesting unit of work. We are starting our work on algebra, okay? Now, today we're going to be looking at the basics of algebra, just an introduction to it to understand what we need to learn before we can move on to solving equations and things like that, okay? So we're looking at basic algebra today and the fundamentals that we need to learn before we can explore it too much further, okay? Let's check it out. Okay, so the very first thing you need to understand is that algebra is very similar to arithmetic. It uses the same 4 operations: addition, subtraction, multiplication, and division. But algebra introduces a brand new aspect, and that is the aspect of the unknown. When you are first looking at arithmetic, the only area that's unknown is the answer. So if we look at a very basic one, 5 add 10 equals unknown. The answer is not known until we go ahead and complete our question. A very important difference straight away between arithmetic and algebra is when we have an unknown in algebra, we use a symbol, okay? Now a very common symbol to be used would be X, but you can pretty much use any letter of the alphabet. X, Y, A and B tend to be the 4 main ones used, but you can use any letter. So in arithmetic, we would leave it as this: 5 plus 10 equals unknown. In algebra, we would have 5 add 10 equals X. The X in this case is a placeholder and it stands for the number that we have not got the answer for yet. So what we have created is a very basic algebraic equation. An equation is just a mathematical term meaning both things are equal. Both things on either side of the equal sign are equal. So it is saying that everything on this side of the equal sign has the same value as everything on this side of the equal sign. So in this example, the equation is telling us that what's on this side, 5 add 10, the known value, has the same value as what's on this side, which is the unknown value that we are going to call X. One of the main aims in algebra is to solve equations. finding out the unknown value, in this case, x. In this example, it's pretty easy to see that we have got 15. 5 add 10 is 15. And all we need to do is add 5 to 10, gives us 15. Therefore, 15 equals x, which is the same as saying x equals 15. Now, this is an extremely easy example of anything to do with algebra. And that is why when you often see algebraic equations, they are a lot harder. And you might be given a much harder example like this. If we had x minus 10 equals 5, that is the exact same equation as if we had 5 add 10 equals x. But it's not quite as easy to tell what x is. So you could look at algebra like a game. You will be given big algebraic equations that it's your job to solve, simplify and find the value of the unknown values. And we are going to learn a lot more about actually solving equations in future videos. So make sure at this point you like and subscribe to the channel to not miss that. But for now, let's learn some very important rules about how symbols can and cannot be used in equations. So the very first rule you need to know is that different symbols or different letters can be used in different problems to represent different values. So for example, in the problem we just solved, the letter X was used to represent the number 15. But X could stand for a different value in a different problem. For example, if someone asked us to solve 5 add X equals 10, the value of the X in this case is 5. Because in order for the two sides of this equation to be equal, 5 would have to add to another 5 to equal 10. So X or any other symbol can stand for different unknown values in different problems. That's fine. But what is not fine is letters cannot stand for different values in the same problem. For example, if we had the expression X add X equals 10, the equation is saying if we add X to X, we get 10. There are a lot of different ways that we can get 10 with 2 digits. We could add 9 to 1, 8 to 2, 7 to 3, and so on. But let's say we represented it as 6 add 4 equals 10. That means the first X, that value is 6. And the second X, that value is 4. This is not okay. This means that different X's would have different values through an equation. And that would become very problematic. So that's not okay. So if you did need to represent two different values in an equation at the same time, you would need to use two different symbols. And that's why we often see X and Y. So if you ever see a really long algebraic equation like this one with lots of X values, all those X values have the same value. Okay, so we know that we cannot have the same letter representing two different numbers. But what about the other way around? Can one number be represented by two letters? Yes, we can. And here's a good example. Let's say we have the equation A plus B equals 2. Now, A could have the value of 0 and B could have the value of 2. Or A could have the value of 1 and B could have the value of 1. Or A could have the value of 2 and B could have the value of 0. So in this example, even though A and B are different symbols, they are holding the same value. There will be times where they just happen to represent the same value. And that brings us on to something else that's really important. Did you notice that each symbol could be represented with a different value, depending on what the other symbol was representing? For example, if A is 0, then B has to be 2. If A is 1, then B has to be 1. And if A is 2, then B has to be 0 in order for the equation to be balanced and to be equal. So a symbol's value can change depending on what the other symbol's values are doing. And this means that it is variable. These symbols are variables. Their value can change depending on what else is happening around them. So in this example, both A and B are both variables because they can both change, their values can both change depending on what the other one is doing. So it's really common in algebra to refer to all letters and all symbols as variables. Okay, so what have we learned so far? We've learned that algebra is very similar to arithmetic. It uses the same four processes: addition, subtraction, multiplication, and division. But we've also learned that algebra has an unknown value that can be replaced by a symbol. And we often see X and Y and A and B being used the most. But there is one more thing that's really important I want to teach you on this video, and it has to do with multiplication. Here are the 4 basic arithmetic problems: addition, subtraction, multiplication, and division. Although in algebra, you will see division being represented in its fraction form. In arithmetic, all 4 of these operations will have the same statue. They are the same importance. However, in algebra, we have a king. Our multiplication is the king. It gets some special treatment. And that's because in algebra, multiplication is the go-to, the standard, the default operation. If you don't see a symbol, you are going to multiply. So therefore, if there are no other arithmetic processes shown between 2 symbols, we are going to multiply. So for example, instead of writing A times B, we can just write AB. And we know that multiplication is implied. Another key word for us. Of course, in this example, we can't actually multiply A and B until we know what values they are. The advantages of this is that it makes a lot of algebraic equations a lot less cluttered and a lot smaller, and you're a lot less likely to make mistakes confusing sometimes X symbol with X the process. So for example, instead of having A times B plus X times Y, we can have AB plus XY. Now this rule doesn't just apply when it's 2 symbols, it is also implied when it's a quantity and a symbol. For example, we don't need to write 2 times X, we can just write 2X. Because there's no other process between them, we are going to imply and we are going to assume it is multiplication. However, we can't use it for just 2 numbers, 2 quantities, because if we wanted to show 2 times 5 and we move the times symbol out, it would show 25. And 25 is not the same as saying 2 times 5. So if we're putting 2 quantities together, we will still see that multiplication sign. But it will still be the case if we are using parentheses or brackets. If we see 2 pairs of brackets or 2 parentheses next to each other, without a symbol, we are going to times them. We're going to multiply the values inside each set of parentheses. For example, if we saw this with A plus B in a bracket and X plus Y in a bracket, with no other symbol between them, we know that we are multiplying the A plus B times X plus Y. So technically what we could do, going back to our 2 times 5, is we could put them in brackets, in parentheses. Therefore, this cannot be confused with the number 25, and we know because there's nothing between them that multiplication is implied. So we would times 2 times 5. Or if we wanted to, because putting 2 separate individual things in brackets does look a bit strange in maths, we could put 1 digit in parentheses and leave 1 out. Again, multiplication is implied because there's no other symbol between it, so we would still do 2 times 5. Okay, so we have learnt that algebra is very similar to arithmetic, but we have unknown values that we need to solve the equation to get to. We've also learnt that in algebra, the multiplication sign is king, and if there's no other sign there, we are going to use that as our default. Now I know what you're thinking, is algebra useful? Why am I learning this? And the answer is yes, they are hugely important. And that's very difficult to see when you're just looking at a bunch of numbers and letters on a page. But when they become very obvious and very helpful is when we start to graph these equations. For example, there is a whole group of algebraic equations that are called linear equations. And that is because they create a straight line across a graph. Those kind of equations are really helpful to tell you the slope of a ramp, or how long it's going to take to get somewhere or do something. Another class called quadratic equations can be used to design telescope lenses, or to describe a trajectory of a ball that's thrown, or predict the growth of population. So algebra is used all the time in fields like science and engineering and other forms of mathematical careers. And if you ever wanted to set up your own business, you would use algebraic equations to work out your profits and work out your potential profits. So this is a really interesting and exciting avenue of maths. Guys, thanks for watching. Check out our next video to begin solving algebraic equations. But for now, like and subscribe to this channel, please. It's really helpful. Maths Hero gone. What's up guys, welcome back to the channel. Matt here again from the Maths Hero, and today we are going to be solving equations. Now if you were lucky enough to catch our last video, you will know that algebra involves variables or unknown values that it's our job to work out. We want to work out the value of these variables. So today we are going to be working out some very simple algebraic equations that involve addition and subtraction. Our next video we're going to look at multiplication and division, but for addition and subtraction, stay tuned. Okay, so if we have an algebraic equation with a variable hidden amongst it somewhere, our main job, our strategy is to isolate that unknown value, get that variable on its own. So basically we want the unknown value on one side of the equal sign and everything else on the other side of the equal sign. And then when we solve it, we'll know just what the unknown value is. Okay, but how? How do we do that? How do we rearrange our algebraic equation so that we put the unknown value on its own? Well, we know that algebra uses the same four operations as arithmetic: addition, subtraction, multiplication, and division. And we are going to use these operations to rearrange our algebraic equation. But stop! There is one very important thing we must always remember and understand, and that is that when we are looking at an equation, it is like a balanced scale. Now we understand a balancing scale. If there are two even weights on either side, the scales are in balance. Okay, so everything on one side of the balance scales has to weigh exactly the same as on the other side of the balancing scales for it to be balanced. If we were to add something to just one side, the scales would become imbalanced. And that is exactly the same in equations. We need to make sure that we are keeping everything on one side of the equal sign exactly the same as everything on the other side of the equal sign. Now that's very important. I'm going to say it again. Everything on one side of the equal sign has to have the same value as whatever is on the other side of the equal sign, because that's what the equal sign means. It means equal to, the same value. Now that does not mean that our equation has to look the same on either side of the equal sign, because we know that two oranges might actually weigh the same as three apples. Even though they look different, they still weigh the same. Well, that's the same as equations. We might have 5 add 5 equals 10. We have different looking things either side of the equal sign, but they hold the same value. 5 add 5 is 10, and the 10 on its own is 10. And it's that word again, value. 5 add 5 has the same value as 10. So this equation is in balance. But why is that important? Well, it's really important to understand that we need to keep both sides of the equation the same, because if we're trying to rearrange them, if we didn't keep that in mind, it would be very easy to add something to one side and forget to add it to the other side, therefore making our equation imbalanced and getting something wrong. So it's very important to understand that if we're going to manipulate or change the equation, we need to do whatever we're going to do to both sides. So I am going to say that again, it is so important. The key is, if we are going to change something in an equation, we have to change the same thing on both sides. If we are going to add 5 to one side of the equation, we must add 5 to the other side for it to remain in balance. And that's the same with subtraction. If we want to subtract something from one side of the equation, we need to make sure we subtract from one side and the other side, because if not, our equation is going to become imbalanced and we will get the wrong answer. Now that is the same for multiplication and division, but we're not quite there yet, so we're going to put that on pause. Okay, so like I said, today we are just going to be focusing on addition and subtraction. And here is our first example. We are going to be looking at x plus 10 equals 18. So let's remember our key strategy. Our strategy is we need to get the x all by itself in this equation. But how? How are we going to do that when at the moment we have a 10 being added to our x? Is there a way we can get rid of this 10? Yes, we could subtract 10, but I can't just subtract 10 on this side. I will have to subtract 10 on the other side. And if we look at it now, if we subtract 10 from our first side that's connected to x, we are left with x on its own, because x, add 10, subtract 10, leaves us with just x. But don't forget, we've now got to answer the other side too. We now have 18, subtract 10, which is 8. Therefore, x equals 8. So, x equals 8 is just a cleaner looking equation to our original question. But if you think about it, we've kind of had 3 lines of answer here. We had the first original question, then we had our extended version where we added in the 2 negative 10s, then we had our final row. Now we're going to start to think a lot about rows as we develop our understanding of equations, because the rows are going to help us understand exactly what we are doing at each phase. Now don't just stop there. If you get an answer, you can check this answer by substituting it into our unknown value. So instead of it saying x add 10 equals 18, we think that x has the value of 8, so therefore 8 add 10 equals 18. We know we've done it correct. Check your work. You've just taken this time to do it. Make sure you got it right. Okay, let's look at another example. Let's have a look at 50 equals 35 plus x. Okay, now in this example, x is on the right-hand side of the equal sign. Does that make it harder? Does that make it any different? Absolutely not. We are going to use exactly the same strategy of just getting our x, our unknown value, on its own. Now in this case, we are having x being added to 35, unlike our first example where 10 was added to x. But thanks to the commutative law, that's exactly the same as saying x add 35. If you're unsure about what the commutative law is, check out our addition and multiplication videos on the channel. Okay, so now it says 50 equals x plus 35. Okay, so in order to isolate the x and get an x on its own, we are going to need to subtract 35 from the second half of our equation. But if we subtract 35 from this side, don't forget, you must subtract 35 from the other side. So our new line says 50 subtract 35 equals x add 35 subtract 35. Now the easy part, we can just go along and solve our equation. We have 50 subtract 35, which leaves us with 15. So therefore the left-hand side is 15. And on this side we have x plus 35 subtract 35, which therefore just leaves x. So therefore we have 15 equals x, which is exactly the same as saying x equals 15. So that's about as hard as addition gets. If something is being added to the unknown, we can undo it by subtracting it. And let's just pause there a second, because I want to just make this really clear. If we have an equation, our main goal is to solve it. And in order to solve it, we can do whatever we want. We can add, subtract, multiply and divide anything we want to it in order to help us solve it. Okay, so that's really important to understand, because some people get a bit confused. Why are we suddenly subtracting a random 25? Well, we're doing that in order to simplify the look of our equation and therefore help us solve it. Okay, so what about when something is being subtracted from our x? For example, x subtract 10 equals 25. So in this case, the x is not alone because the 10 is being subtracted from it. If we want to get rid of that 10, guess what we need to do? That's right, we need to add a 10. So our new line reads x subtract 10 add 10 equals 25. Good, don't forget, make sure whatever we do to one side, we have to do to the other. So if we've included this add 10 to the first side, we need to add it to the second side too. So it reads equals 25 add 10. Therefore, our x is now on its own because plus 10 minus 10 leaves us with nothing. So x equals 25 add 10, which is 35. X equals 35. Easy. Okay, let's look at another example. Let's have a look at 5 equals x minus 22. So in order to get rid of that negative 22, we need to add a 22. And don't forget, we need to do that to both sides. So what does our new line read? Our line reads 5 add 22 equals x subtract 22 add 22. Therefore, when we start to solve it, we can see that 5 added to 22 is 27. 27 equals x, and the negative 22 and the add 22 cancel each other out. Therefore, 27 equals x, or x equals 27. Great, we are getting good at this. Okay, now we are getting really good. You now know how to solve really basic equations like these, where something is either being added to the unknown or where something is being subtracted from the unknown. Okay? But stop. We have got a small issue. Remember that cheeky little word I told you about, commutative? Well, addition is commutative, but subtraction is not. So what happens, instead of something being subtracted from the x, what happens if x is subtracted from a value? Now we've got a little complication. Okay, so let's have a look at an example. If we had 10 subtract x equals 5. Now, if we look at this carefully, the subtraction, the minus sign, is actually connected to the x because that's what's being taken away from the 10, which therefore means the 10 is a positive. Now we still want to get the x on its own, so we can get rid of that 10 by subtracting a 10 from both sides. That's fine, that's going to get rid of the 10, but it's still going to leave us with the minus sign. That's fine, we can have a minus x, but that's going to get very confusing if we don't know how to use negative numbers. So there is a better way. Let's check it out. So here's our next step for understanding how to solve equations. It is not just values that we can add, subtract, multiply and divide onto both sides. We can also do that to the variables, the unknown values. So instead of subtracting the 10, we can look at the x. We have a negative x. How do we get rid of a negative x? We add an x. So we're going to add an x to this side, which is going to put an x on our other side, which then we can isolate in a moment. Remember when we spoke about rows in solving our equations? This is now adding another row, okay? We've got another phase to this problem. So let's go ahead and do that then. Let's add an x to this side and add an x to our other side. And remember, we can do that because we can do whatever we want. We can add anything and subtract anything from either side as long as we do it to both sides. That's our really important lesson today, okay? So we can add anything, including variables, and subtract anything, including variables, okay? So let's go ahead and put that in now. So now we read 10 minus x, add x, equals 5, add x. Okay, so now our next row, our x's are cancelled out, and we have 10 equals 5, add x. Now you might be thinking, why have we just done that? That's added another phase. Well, the reason is because we now have an equation that we know how to solve. This looks very familiar, doesn't it? We can do this using our original and key strategy of isolating the x. So at the minute, the x is being added to a 5. So in order to get rid of that 5, we are going to need to subtract a 5 from that side. If we're going to subtract a 5 from that side, we are going to need to subtract a 5 from the other side too. And don't forget that it doesn't matter which way around we put our addition because addition is commutative. So 5 add x is the same as saying x add 5. So let's rearrange it so it looks a bit easier. 10 equals x plus 5. Now we want to get rid of that plus 5. How are we going to do that? That's right, subtract 5. So we're going to subtract 5 from this side, we need to subtract 5 from this side too. So 10 subtract 5 equals x, add 5, subtract 5. The two 5's on this side cancel each other out, therefore 5 equals x, or x equals 5. Solved. We are amazing. This problem just took us one extra step to solve this equation, but that's okay. Bigger equations are going to have even more steps. So it's really important to start understanding why we put the rows. Okay, so let's recap. We now know the basics to solving equations that involve addition and subtraction. The key feature, the key strategy is to get the unknown value on its own. And we can do that by manipulating the equation, by adding or subtracting to cancel out any value that might be in there. But remember, the important rule, anything you do to one side, you must do to the other. You must do both sides. Now don't forget, it's really important to practice, so have a little Google, get some questions up there and have a practice of solving addition and subtraction basic equations, okay? Check out our next video for multiplying and dividing basic fractions. I hope you've enjoyed this, I hope you've learned something. Thank you very much. Like and subscribe to this channel, really appreciate it. But for now, I'm gone.
What's up guys, welcome back. I've got a brand new video. Today we are looking at multi-digit multiplication. So that is a multiple digit multiplied by a multiple digit. Okay, this is pretty high-end stuff, so check it out. Right, first first, what is a multi-digit? Well, a multi-digit is any number greater than 9. So for example, 10, 11, 53, these are all multi-digit because they have more than one digit. Okay, the number 4 is just a single digit because it's just one digit on its own. And we can go all the way from 10 to infinity will all be multi-digit numbers because they're all going to have multiple digits going along the place value chart. Okay, so that's very important to understand before we start. The reason that place value is so important to understand before we start is because we're going to use our understanding of place value to partition and break up our multiple digit so that it's back into more manageable chunks that are easier for us to multiply. But before we get into it, let's review what we've done so far in previous videos to understand where we're at now, okay? So our written method started with grid method. Now grid method was really useful because it really showed us what we're doing. We're breaking up those numbers and we're answering them in smaller chunks and then putting that number back at the end to give us our final total. Okay, so that was the start, but it was a bit long. We realised that when we got into bigger numbers, it got a bit long and a little bit laborious. So then we moved into formal written method, which is our columns. Okay, but we looked at first at expanded method, which was a bit like grid method, but looking at it in the formal written method. So we still partitioned every part and we still wrote down each individual question and did them in 4 or 5 different rows. Okay, again, a good method for understanding our cognitive understanding and our understanding of what's happening, but it was a bit long. And our method after that still looked at multiple digit multiplied by a single digit, and we did it quicker using a similar method to say addition or subtraction, where we stayed on one row to answer each individual part. So if we were looking at 32 times 5, that first row would have 5 times 32 all in the first row, rather than having a second row for 5 times 2 and then the second row for 5 times 3. Okay, that was another step forward, but now we're at our ultimate step. We're going to add a multi-digit to the second part too, so it's going to be a multi-digit times a multi-digit, okay? It is a leg up, it is our next progression, and there is a little trick to it, something that we need to learn and something that we need to understand, okay? So, let's start. Let's have a look at a green chili challenge. So let's use the example 32 times 25. And we're going to start at our smallest value, but it's really important to understand what we're doing. Our first row is actually going to use this unit here times by 32, so it's going to be 5 times 32. And our second row, our last row, is going to be 20, which is what this 2 represents, 20 times 32. And then we're going to add them together. So we're still partitioning it, but we're doing it a little more discreetly. And if we're not exactly sure what we're doing, we might make small mistakes, which is why it's really important at this stage to really understand exactly what we're doing and where our numbers and answers are coming from, rather than just following a process. So let's start together. Let's do 5 times 2. Well, 5 times 2 is 10. So let's put our 10 in as we would do now if we were doing, say, for example, an addition or subtraction question at our shortest method. So I'm going to put my 1 into my tens column as a small little 1, just so I can remember to add it to my tens column when I do that, but I'm going to put my 0 in my units column. Now I can move on to my second part of the question, 5 times 3. Well, 5 times 3 is 15. I've got no hundreds, so I can just put the answer straight in there, but I must remember to add on that 1 that I had in my tens column from before. So 15 plus 1 is 16. So the answer to 5 times 32 is 160. Okay? So, good. We've done that first row. Now I'm going to do 20 times 32, but I don't want to look at it as a 20, and here's the thing that's going to get tricky. Okay? Here's the thing that we need to understand. Here's the difference between this method and our previous method in terms of how hard it is. Okay, so we're going to include what's called a placeholder, because we want this whole question to be 10 times smaller to work with. We don't want to work with 20 times 32, we're going to still do 2 times 32. And to make it 2 times 32, we're going to make our answer 10 times larger, because we know it's not a 2, it's actually a 20. So let's make our answer 10 times larger by putting a placeholder. I'm sure you've all done this, but you might not be sure why. Okay, so we're putting this placeholder in there because if we do 2 times 32, we need our answer to actually be 10 times larger than that. Okay, so put this placeholder in there. Now I can treat it like 2 times 32 again. 2 times 2 is 4. Put my 4 in the next available column, which is my tens column. And again, this is where some people might make mistakes because they think, well, I've just put my 0 in my units column, but I always meant to put my answer in my units column. Well, that 0 is holding the place of the units, okay, because we're 10 times larger. So our next space is tens. 2 times 2 is 4. And we can check that because 2 times 20 is 40. And that's what it said. Cool, we know we're doing something right. Okay, so the next part says 2 times 3, which is 6. Put that in there, 640. Are we finished? No. Anyone who's done partitioning before knows we've only done the individual elements. Now we're going to put it back together. Again, starting our units, 0 and 0 is 0. 6 add 4 is 10. Remember to move the 1 across. 1 add 6 is 7, plus the 1, 8. 800, okay? 32 times 25 is 800, and that's a green chili challenge. Okay, let's look at an orange chili challenge. Now at this point, I want to highlight something. I want to talk to you about something, an expression we're going to use quite a lot, and that is it harder or is it just longer? Okay, now in this example for the orange chili challenge, I pose to you that it's actually just a little bit longer. This isn't harder, what I'm about to show you, but it's just a little bit longer. And I've given it an orange chili because the only thing we need to understand today really is why this is only longer and not harder. So I've given it orange, although it is actually still probably only a green challenge. Okay, so let's have a look at it. It's 482 times 24. Okay, now let's think back to our understanding of what we're doing. We are breaking this number down into more manageable chunks. So we're going to isolate those two numbers again on the bottom row, and we're going to break it up and we're going to multiply the top row by it in little chunks. Okay, so my 4 is going to times 482 first, which is going to make that first row, and my second row is going to be 20 times 482. Okay, but remember we're going to add that placeholder to make it 10 times larger, so we can just do 2 times 482. Okay, so this is only longer because we've only added a digit to the top line. And we're going to see what happens when we add a digit to the bottom line in a moment. But let's answer this challenge first of all then. So 482 times 24. Start at our smallest value, and we're going to start with the 4 times 2. 4 times 2 is 8. Then we're going to move across. 4 times 8. 4 times 8 is 32. Add 3 across into my hundreds column and 2 into my tens. Good. 4 times 4 is 16. Add the 3, 19. So my answer to 482 times 4 is 1928 and completes that first row. Now, my next question is 20 times 482. So we don't like 20, so let's make it 10 times smaller and put it as a 2, but that means we need to make our answer 10 times larger so we actually get the correct answer. So I'm going to put my placeholder in place, okay, great. Now it's just going to be 2 times 482. So 2 times 2 is 4, add that in. 2 times 8 is 16, put the 1 across, put my 6 in place, good. 2 times 4 is 8, plus the 1, 9. 9,640. Now here's something really important. Look at these extra numbers that we've got in here. These were helping us solve previous parts of the question, and we should have put a line through them when we're finished with them, okay, like I have. And we must remember at this point we do not add it to our total because those numbers have already been used and we've already got them added to whatever we needed them for, okay? So we don't want to add them again now, so let's make sure we don't do that, guys. That's really, really important, a top tip. Okay, and remember, add it together, so put my line across, make sure I add it. 8 add 0 is 8, 2 add 4 is 6, 9 add 6 is 15, move my 1 across, put my 5 in place, and then 1 add 9 is 10, plus the 1 is 11. 11,568, and that is your orange chili challenge done. Okay, final stage, our red chili challenge. Now we are going to make this harder this time because there's an extra element we need to understand, okay? So I'm going to give us the question, 452 times 235. Now these are huge numbers now, so we've got to be really careful and we've got to be really precise. So we're going to carry on like we did before, and we're going to understand that we're going to partition it all, okay? So all we're doing for this first line, for this first row, is we're still multiplying 5 by 452. Okay, so 5 times 2 is 10, good. 5 times 5 is 25, add the 1 is 26. 5 times 4 is 20, add the 2 is 22. So our first row, 5 times 462, is 2,260. Okay, right, now our second row, same as before, we are now looking at this 3, but it's not a 3, it's a 30, so let's make it 10 times larger by putting in our placeholder, okay, because it's a 30. It's 10 times larger than 3, which is what we want to be dealing with. Okay, so just like before, 3 times 2 is 6, 3 times 5 is 15, 3 times 4 is 12, plus the 1, 13. So 30 times 462 is 13,560. Okay, great. Now, we've got an extra number. We've got this 2, this 200 here, okay? Now we want to do just like before and multiply it by the top row, so we're going to do 200 times 452, but I need to think about my placeholders because I can't just put one placeholder because that would mean the 2 actually turns to a 20. But it's not a 20, it's a 200. It's in our hundreds column. So I need, that's right, 2 placeholders, okay? Because 200 is 100 times larger than 2, the number we're actually going to be multiplying with, okay? So I need to put 2 placeholders in now. Now we can just carry on like before. 2 times 2 is 4, making sure I put it in the correct column because I've now got 2 placeholders occupying the units and the tens column, so I'm going to put this straight into the hundreds column. So 2 times 2 is 4, and I can check that because 200 times 2 is 400. Okay, great. 2 times 5 is 10, so we've got a 1 across and put our 0 in the right place. And 2 times 4 is 8, add the 1 is 9. Okay, great, we've just done our third row. Okay, let's make sure we add it up. So 0 plus 0 plus 0 is 0, obviously. 6 plus 6 is 12, making sure not to include that other 1. 2 plus 5 plus 4 plus that 1 is another 12. And then 2 plus 3, add the spare 1 is 6. 1 plus 9 is 10. So we get 106,220. Now, anything beyond this level is just going to be longer. Now we can have a 4-digit number multiplied by a 4-digit number, and all that's going to do is add another row where we need to add 3 placeholders because we're looking at thousands now. We could look at a million times a million if we wanted to, okay? It's not going to make it any harder, it's just going to make it longer. But don't forget, sometimes when we do things longer, we might make mistakes. So it's really important that we check our work and are really, really careful, okay guys? Well done. So let's recap some really important things from today, guys. First of all, it's really important to put our layout and our numbers in the correct columns. This is really, really important today because we've got such a huge amount of numbers that we're going to be multiplying, and when you get into 4-digit numbers or 5-digit numbers and anything like that, you actually get a really big area where your answer is, and it comes out in like a triangle formation as the number gets bigger and bigger. So if you're not in the right columns, it can look really messy and almost be impossible to make sure at the end when you're trying to add up, you're adding up the correct columns. So organisation and layout is really important. The second thing to understand is knowledge of partitioning and knowledge of place value. Understanding that when we're timesing 32 by 25, we can break it down into those smaller chunks and understand what chunks we are actually multiplying at the time. Okay? Next thing to remember is our placeholders. Placeholders are hugely important to understand, not just to do, but to understand, okay? We need to understand what we're doing. If we're doing 25 times 32, and we've got the 32 on the top and the 25 underneath, then we need to understand that when we come over to that 2 part and we're timesing the 2 by 32, then it's not a 2, it's a 20. Okay, we're only wanting it to be a 2 because 2 is easier to multiply. Okay, so if we are making it a 2, we've actually made it 10 times smaller. Okay, so when we make our answer, we need our answer to actually be 10 times larger, what it's supposed to be. Okay, so placeholders are really important to understand. And the final thing, final recap, make sure that when we've done our answer, we don't just finish with the partitioned answer, we actually add it together to give us our grand total, because that's what we're looking for. We're not looking at for the partition numbers, we're looking for that grand total. Okay, well done. Right, I'm going to put some questions for you on the board here, guys. I'm going to put 4 questions. There's a green, an orange, and a red. So challenge yourself. If you get all 4 of these right, you are ready for our next step, and that is multiplying decimals. That is our next step, our next progression in our understanding of multiplying. Well done, say guys, thanks very much. Make sure to check out the rest of our videos on the channel for all your mathematical needs, and give us a subscribe if you've liked this video, guys, because there's going to be plenty more like this. Okay, thanks very much, guys, but for now, Math Zero gone. What's up, guys? Matt the Maths Hero here, and I am looking at short division today with a brand new video. Let's check it out. Right, before we can start, we need to think about what division actually means. Well, if I pull this question up, 12 divided by 3, we will learn that we can talk about division in 2 different ways. We can talk about it as sharing. If I have 12 lollipops, I can share them evenly between my 3 friends, giving them a total of 4 each, so 12 divided by 3, 12 shared by 3 is 4. Or I can look at it as grouping. How many groups of 3 are there in 12? That's a slightly more advanced level. Well, let's have a think. There's 1 group of 3 and 3, 2 groups of 3 and 6, 3 groups of 3 and 9, and 4 groups of 3 in 12. So we can look at it in 2 different ways, sharing and grouping. Now, the reason that a question like 12 divided by 3 is quite straightforward is because 12 divided by 3 is part of a number family. 12 divided by 3 is 4, and 4 times 3 is 12. They are in the number families. But what happens if these questions get a little bit harder and they're not in number families? Let's have a question like 14 divided by 3. Well, we can try and share them. I've got my 14 lollipops and my 3 friends. I'm going to share them evenly. Gives them 4 each again with these 2 left over. Now these 2 left over are very important. I cannot share them evenly between my friends, so we have to leave it as a remainder. So 14 divided by 3 would be 4 remainder 2. If I try that with grouping, it would be the same thing. 3, 6, 9, 12, 4 even groups and 2 left over. Okay, 2 remaining. Okay, now that's pretty straightforward with small numbers. We can easily share our lollipops out. Might take a little while, but we can do it. And I can group because I know my times tables, okay? But what happens if we get a bigger question? Let's have a look at a green chili challenge. Let's have a look at 248 divided by 2. Now, I don't want to share out 248 lollipops. That's going to take me all day. And I don't want to have to go over my 2 times table all the way to 248. Again, that's going to take me a long time. So we need another method. This method is called the bus stop method. Now, we call it the bus stop because it looks a little bit like a bus stop. Now, we need to know, before we can start, we need to know where we are going to put our features, our parts of our question. So I'm going to put the dividend, which is the big number, the number we are trying to break up and share. I'm going to put that inside the bus stop. So I'm going to put my 248 inside my bus stop. Now I'm going to put my divisor on the outside, the small number, the one we are sharing the bigger number into. Okay, so my question now looks like this. How many 2's are there in 248? Okay, now before we can start actually solving this, let's think about our layout again. Let's put our hundreds, tens and units in to help us just understand what actually is happening, okay? Because we are going to start dividing along our bus stop, but I want us to understand exactly where our numbers are coming from and the actual real true value of our answer, okay? So, if we're going to look at this first part, 2 divided by 2, how many 2's are there in 2? Let's share it out. How many 2's are there in 2? Well, it's 1. We can share it evenly once. Okay, so how many 2's are there in 2? There are 1. Okay, but the question actually said, how many 2's are there in 200? And the answer is actually 100. Okay, so let's just keep that in the back of our minds just for our own understanding, okay? Now, the second part, how many 2's are there in 4? Well, if I share 4 between 2 people, I give them 2 each. So my answer for that section is 2. Last bit, how many 2's are there in 8? Well, the answer is 4, giving me a grand total of 124. Let's drag that back up to complete our question. 248 divided by 2 is 124. Great, green chili challenge, done. Okay, let's have a look where this can go. Let's have a look at a red chili challenge because they're not always going to be as easy as that. We could get complications as we're going to see now, okay? Let's have a look at 896 divided by 5. We're going to put our hundreds, tens and units up there just for our own understanding, but we're going to start in the same way. How many 5's are in 8? Okay, now let's go in our 5 times table. 5, 10. So we can't have 10. We've got one lot of 5, but then we've got 3 left over. Okay, let's have a look at that in sharing. If I have 8 and I try and share it evenly between 5, I give them all 1, but I've got 3 left over. Now I can't ignore this 3. I'm going to move it over into my next column and make my 9 a 39, okay? Because that 3 is actually worth 3 10s, okay? That's why it's good to understand our columns. Okay, let's look at my second part then. So how many 5's are there in 39? Let's go up in our 5 times table. 5, 10, 15, 20, 25, 30, 35, 40. I can't use 40 because it's over 39, so let's come back. 35 goes 7 times. So I'm going to put 7 at the top there. But what have I got remaining? I've got 4 remaining. Okay, so I'm going to bring that 4 over into my next column. Okay, last bit says how many 5's are there in 46? Again, let's do the same thing. 5, 10, 15, 20, 25, 30, 35, 40, 45. Can't go to 50, so I've got 9. What's the difference between 45 and 46? I've got 1 left over. So my answer is 179, remainder 1. 896 divided by 5 is 179, remainder 1. Okay, that's about as hard as short division you can go. That is a red chili challenge. So I'm going to put these 3 questions up on the board. Take your time, have a little go at them, put your answers in the comment section below. Let's see if you get them right. If you do, fantastic, let's move on. If not, take a little bit of time on this video and make sure you fully understand it before moving into our next video, okay? So I'm gonna put the answers up in 5, 4, 3, 2, 1. Okay, answers on the board, fantastic. Well done if you got them right. As I say, let's move into our next video then. If not, rewind, go back, see where you might have made a mistake and correct yourself, okay? It's all about making sure you've got a great understanding before moving into our next step. So what is our next step? We have been looking at short division today. A multi-digit number divided by a single-digit number. Well, long division, our next step, is going to be looking at a multi-digit number divided by a multi-digit number, okay? So if you're ready for that, check out our next video. Thanks very much, guys. I hope you've learned something today. Like and subscribe to this channel. It's very, very helpful. Thank you very much. Away.